Okay. So we looked at the single balance mixer last class. Okay. So for today's class, we'll look at the what is called the double balance mixer, and then we'll look at the different options for transconductors. Okay. If you have time, we'll move on to linearity of the mixer. Next class, we'll do noise. Okay. Okay, remember we talked about this last class. This class of mixers are called Gilbert mixers because the basic cell they use is called a Gilbert multiplier. Okay. Okay. So the conversion gain we saw last class from the RF voltage to the RF current was 2 by pi GM for the single balance mixer. Okay, and this of course assumes you have perfect switching, right, and that they are perfectly matched. Those two things are assumptions. Okay, so first of all, let's look at what would the load look like. So let's say you have a TX, a transmitter. So you have the baseband signal. Yes. So this is a direct conversion transmitter where you have the baseband signal which is being directly converted to RF through the LO. Okay, there's no intermediate IF. Okay, so what would this look like? So at the input you can have a simple transconductor. Okay, you don't have any bandwidth limitations, so your signal is very low frequency. So let's start off with that. Okay. Okay, how about the load? Output frequency is pretty high. Okay, so you probably can't use resistive loads because your RC bandwidth will be much smaller. Okay, so what do you want to use? You want to use tuned loads. You have some capacitance C. Let me call it L over 2, L over 2. Okay, so this, as far as the signal is concerned, you can approximate this to an LC tank with some parallel resistance Rp. Sorry, good point. And the output comes out of here. Okay. Okay, the output is a differential resistive output. So the voltage to voltage conversion gain is going to be 2 by pi GM Rp, where Rp is the inherent parallel resistance of the tank. So remember, in all of these narrowband circuits, this Rp is actually a fictional, you don't add it yourself. Okay, it comes because the capacitance and the inductance have their own Qs. Okay, and you can replace each one of those components by the ideal component in parallel with the resistance. Okay, which stands for the losses or the Q of the inductor or the capacitor. And so this is the overall parallel resistance. Okay, so that's easy. How about a receiver? Oh, sorry. So last class we looked at the what is the transmit output spectrum, right? So if you have a receiver, okay, so you're going to have omega LO. Okay, So at the baseband you're going to have, or rather at the IF. So let's say, of course, since this is a single balance mixer, you're going to get your omega LO, and let's say your omega IF is somewhere here. This is omega LO plus omega IF. Okay. I'm just going to expand this guy. So you'll have the third harmonic, and around the third harmonic you're going to have the same thing. Okay, each one of these harmonics will mix with the RF to give a component around that. Okay, so you get the idea. So what you need is actually a filter which looks like this, something like this, right? IF is much smaller than LO and 3 omega LO and so on. Okay, so which means, so if IF is large enough, you can use LC loads. Okay, let's say IF is a few hundred megahertz, you may be able to use LC loads. But if IF is, let's say, 100 megahertz or something, the inductor and the capacitor values will become too big for you to use anything. You'd be much better off using RC loads. Okay. It depends on the frequency whether you want to use RC or LC. Okay, if your IF is very low, anywhere from a few tens of megahertz to maybe 150 200 megahertz, you'd want to use RC. Okay, you probably get enough bandwidth to do an RC. Also, the LC is going to become pretty big. The inductance value you might get tens of nanohenries probably. Okay, and of course the conversion gain is again 2 by pi GMRL. That's pretty straightforward. Okay. In this case, you can use an LC tank if the frequency is large enough. Sure, if your IF, so let's say you're transmitting a signal at 5 gigahertz, so your LO may be around 5.1 or 5.2 or whatever, 5.5 let's say, and your IF frequency is 500 megahertz. You may be able to use an LC tank. Okay.
This does not have very narrow band properties there.
RC, of course it does. You can choose your RC. So remember the case what I was saying. So this is, let's say, 100 megahertz. So this is maybe 2 gigahertz. You can easily get a good enough RC filter, right? And so what that means is your LO feed through is not a big major problem. Last week we saw that for the TX mixer, the LO feed through was a big problem, right? Because it falls right next to your RF. For this guy, and omega baseband is very small, right? So your LO falls right next to your RF. So that is a problem. In the case of a receiver, depending on your IF frequency, it may not be a major problem. Sorry? Gain is a function of? Of what? Sorry? Oh, of LO power. Right now we are assuming that you are in this case, right? Remember that we assume that the current is completely switched between both sides. So that is how you get the 2 by pi factor, right, from last class. Otherwise it's not a function of LO power. Okay, we assume that the LO is large enough to completely switch the currents and fast, immediate and perfect switching. Once you have that, it's no longer a function of your LO amplitude. Okay, that is something we assumed. We'll look at whether that's really true. I mean, whether how we decide the LO amplitude, we'll look at that either later this class or next class. We'll look at it. Is there an advantage? Sure. I mean, there is an advantage in the sense you don't have to be limited on your LO side to have a specific amplitude. If see many of these things, if you want to drive with an exact amplitude, so if you want to get a gain, so gain of 20 dB, let's say, your margin on how accurate your gain should be will be probably plus or minus 1 dB. Okay, so obviously if your LO varies by a lot over process, and it probably will, then you have a problem. Okay, so you may want if gain depends on LO, then you need to control it very well. That is the only problem. Otherwise, there is no. Apart from that, I can't think of any other major problem with that. Okay, LO to IF isolation is not a problem here. Okay, so now let's look at how you combat LO to IF isolation.
Sir,
Yes.
when we are not going for high frequency,
Yes.
at the output, why not we can use demos also?
We will come to that. That is one of the other things we'll be discussing. Okay, we'll probably, I thought I'll include that with noise. Okay, but this is the kind of the most basic thing. We'll include some PMOS load options with noise. Of course, you can do that. Okay, there are a lot of options. This is the most basic option, RC. So the reason you would want to use PMOS loads, of course, is because of headroom. Okay, so there is a gain versus headroom trade-off, right? Very obviously with R. I mean, you would have studied this in differential amplifiers, right? The reason why you move to PMOS loads is because of that. So same thing, holds good here. Okay, so we look at the double balance mixer. So let's take a look at this structure. So this is basically just two single balance mixers, except that, so in the earlier case we assume this is IDC plus IRF cos omega RFT. We'll assume that the other side is IDC minus IRF cos omega RFT. Okay. So let's label the currents and see what it looks like. So I1, I2, I3 and I4. Okay. So what is I1 minus I2? We already know this, right? This is just a single balance mixer. I1 minus I2 is just the differential output of the single balance mixer. Times SFT. SFTs are switching function, right? The signum function. Okay. Now note the sign. Obviously, it's this on this side because VLO plus goes here. I4 minus I3 is IDC minus Okay, so this is I4 minus I3 is IDC minus IRF cos omega RFT times SFT. Okay, what is IO1? Is I1 plus I3. Okay, IO2 is I2 plus I4. Okay, so what is the differential output current is IO1 minus IO2. So what is this? So we'll just rewrite it slightly differently. So this is I1 minus I2 minus I4 minus I3. Okay, so what is this? So this minus this, right? So the IDC gets cancelled and you get 2 IRF cos omega RFT times SFT. Okay, so note one very important thing. Earlier in the single balance mixer, you are getting your LO component at the output because IDC was getting multiplied with SFT. Remember that? So IDC has obviously has no frequency component, it's DC. Multiplied with SFT has components at omega LO, 3 omega LO, 5 omega LO and so on. So at the output you get components at all of these frequencies. In this case you no longer have IDC, you just have IRF times your frequency. Okay, so this is, so remember that SFT has a magnitude of 2 over pi, so this becomes 4 IRF over pi times, so you have cos omega RFT multiplied with omega LO 1/3 3 omega LO, 1/5 5 omega LO and so on. Okay, so that is okay, sine of omega LO minus omega RFT and omega LO plus omega RFT. So that's the multiplication with the fundamental. Sorry. Okay, you will have the fifth, 1/5 the fifth harmonic and so on. Okay, so you have excellent LO isolation, LO to IF isolation, but obviously we have assumed that everything is perfectly matched, and just like your RF isolation in the single balance mixer depends on your matching, your LO isolation here will depend on your matching between the two differential paths. Okay, so let's look at the, so if you look at your so we just assumed a current source, right, IDC plus IRF. How would you implement that? So your true double balanced Gilbert cell mixer would look like this. Very bad. Okay, so now, so what we are going to do is put in the diff pair here. And you're probably going to have a current source here. Okay, current source, obviously it's going to have 2 IDC now. Okay. So obviously one problem is now you have headroom loss due to whatever. If you have a PMOS here, it's PMOS. Okay, you have stacking of 3 transistors. Okay, that is something you can't do much about. You can try to reduce it down to 2. We'll look at that. Okay, what is the conversion gain? So what is the output amplitude? Amplitude of the IF is 4 IRF over pi. Okay, of course times, that is just the current, so times RL by the input RF amplitude. Okay, what did we assume here? So we assume that there is IRF here and there is an IRF here, right? So your input signal, if you should actually be 2 VRF, right? Okay, so the conversion gain is again 2 by pi GMRL. There is no difference between the single balance and the double balance mixer in terms of conversion gain. Okay. Okay. How about LO to IF isolation? So it depends on matching, right? Okay, depends on matching. Some quick numbers to keep in mind, right? If you have 1% matching, this gives you around 40 dB of isolation. Okay. Between the two paths, the two differential paths of RF. Okay, between VRF plus and VRF minus paths, if you have around 1% matching, that will give you around 40 dB of isolation. Okay, similarly, if you have matching issues between the LO, VLO plus and VLO minus paths, that will give you RF feed through. Okay. And if you use really good layout techniques, okay, so you can probably get somewhere around 0.1% matching. This will give you around 60 dB. Okay, but you'll need to use good layout techniques. We'll look at that at the end of this course. I'll have one class on layout, RF and analog layout. I don't know, have you covered analog layout in any course at all? No, not yet. Okay.
The current source transistor matching?
It is your VRF plus and VRF minus paths. Well, in this case, it's these two paths, because that is what is creating your IR and minus IRF. Okay, so what are the sources of mismatch? So you have delta W and delta L. Those are the differences in width and length, and that is usually caused due to photolithography, right? Errors in litho. Then you have delta VT mismatches, the threshold voltage mismatches. Okay, what is that caused due to? It's your doping, right? Then your T-ox and C-ox. Actually, C-ox itself also depends on epsilon ox. So let's, okay, it's T-ox and epsilon ox. And of course, again, you also have C-ox mismatches because of this. Okay, so mismatches in all of these can cause problems with isolation. Okay, so let's look at some. So in the transmitter, it's somewhat straightforward, right? So you don't need a lot of bandwidth from your baseband, the transconductor. That's a little bit more straightforward. But we'll look at something which is more oriented towards receivers. But several of these things can also be used with transmitters. Okay. So let's look at the common source stage. So first thing we'll do is put an inductor at the source for degeneration. Okay, what you'll see is at least several architectures, whatever topologies of transconductors would use some kind of degeneration, resistive or inductive. Okay, and you have RS. This is your RF source. You have the RS, and you have some blocking cap CB, and you have some V bias through some R bias. And of course, we'll assume R bias is much larger and CB is much large enough such that it doesn't matter, right? Okay. So let's look at IRF versus VRF. Okay, which means GM effective. Okay. Obviously, the low frequency GM is just GM. So you have 1 plus. Okay, and you're going to have a second order because now you also have CGS and LS. S square. This is going to be your denominator. Okay, so the other things to note are, of course, the reason we use inductors, no noise. If you add resistors, you have thermal noise. Inductors will have very little noise. Second thing, very little headroom. Okay, depends on your, in the case of resistors, depends on your bias current. In the case of inductors, independent of your bias current, you don't have any headroom at all. So those are two very important advantages. Okay, and there is one third advantage, which is the fact that the impedance of LS increases with frequency. It's omega times LS, right? So at very high frequencies, you will have very good attenuation. Okay, because this LS is a high impedance, so you can't have any high frequency current flowing through this path, through the transistor. Okay. Okay, so this is GM, and note that this is a two-pole roll-off at some frequency. So which means minus 40 dB per decade. Okay. Okay, but one thing you have to remember is this is very good if you are driving with something which is matched to 50 ohms, which means you use this LS to again match it to 50 ohms at the input. You'll probably need to use an LG also if you want to get it at the right frequency. Okay, so you'll have something similar. Now if you try to drive this with an LNA which is used to driving a capacitive load, like what we are going to design in the project 2, what will happen is this transconductance stage will have an input resistance of omega d times LS. okay, at all frequencies, okay, at all frequencies below omega t, of course. So what that means is that could very well DQ the LC tank of your LNA. So when you put the two together, you will start seeing problems, okay. Okay, so let's look at the common gate stage. So you have some current here, IDC. Okay, you have the source resistance and it goes directly into the source of the transistor. And again this RS acts like a degeneration for the transistor. So this is your 1 plus GMRS is your low frequency component, and then you also have an SCS RGS, sorry, SRS CGS, okay. Okay, what is the pole frequency of this? By RSCGS. So which is approximately omega t, okay. So which means it's a pretty wide band stage, but the gain is somewhat lower.
This is just the basic common gate.
Yes, except that we have just taken it upon CGS, that's all. The normal common gate at low frequencies, you know, it has GM over 1 plus GMRS, right? And at omega t, and it has a 20 dB per decade. Now the reason why this pole roll-off matters is if you are more interested in cutting off high frequency harmonics, okay, high frequency components, then you probably want to, this will give you some limited amount of this thing, right? This will give you some limited amount of attenuation, but the common source will give you much better. But if you are interested more in wideband, then the other one will give you much better. And of course, if GM is large enough, if GMRS is large enough, this is approximately 1 over RS. That's why it's a lot lower than the other case. Okay. So that is for a single balance. So we looked at single-ended transconductors. In the case of a double balance case, you want a differential transconductor. Okay, so let's look at that. So of course you can just put two of these together. Okay, and of course LS is optional, that's always the case, right? So don't worry about that. And the good thing about going differential is you get better CMRR, okay, fully differential, you get better CMRR at low frequencies. Obviously at high frequencies what happens is, because of this current source or other things, you will have some parasitic capacitance here, and that will limit your CMRR. So once you go beyond a certain frequency, your CMRR starts dropping until it goes down to 0 dB at very high frequencies. Okay. Okay, and of course the differential current has, has no even harmonics, so those are all very common things for differential circuits. Okay, and it has a significant third order component, those are all very common. Okay. Now you can do even better than this in terms of headroom. Why? Because you need probably you need some VD-SAT here. Minimum of one VD-SAT you need here. So you can also get rid of that. So you can get rid of the current source completely and use what is called a pseudo differential or completely balanced stage. Okay. Okay. So you can just take two single-ended stages and put them together, drive one with RF plus, the other with RF minus. Okay. And this is becoming actually fairly popular because you really cannot do it, more than with, as you keep, like in your case, you're using 1.2 volts, right? So with that, you really can't stack more than a couple of transistors for effective operation. Okay. Of course, the value give up is CMRR is 0 dB for all frequencies. You are basically relying just on completely on the matching between the two sides. No, in the other case, okay. So in the other case, it depends on matching, but it also depends on the impedance. Remember, the CMRR of a differential stage depends on the output impedance of the current source. Remember that? So in this case, it's of the tail source, right? So in that case, you would have pretty good CMRR, at least at low frequencies. In this case, your CMRR is pretty much 0. Yes, of course. No, what I'm saying is it doesn't have to do with the input. Okay, why do you need CMRR in general? It is not necessarily because just the common, so it's not just because of common mode from the input. You also have common mode coupling from the supply and the ground, right? That's the reason why you would need it. So this case, you are completely, so if you have some, let's say some signal on the supply or the ground, right, that could very well happen. You could have signal coupling in through the substrate, the ground, the supply, any one of these common points, and you are completely relying on your matching to do your, for it not to appear at the output. Okay. What is the other thing you know? Assume that these are square law MOSFETs. Okay. If you assume these are square law MOSFETs, okay, that means that there is no third order component at the output. Okay. Which means effectively your IIP3 is infinite. If you have a perfect square law device, your IIP3 is infinite for this guy. Okay. In the case of differential, that's not true because you have a relation between VGS1 and VGS2, so that automatically makes you have all harmonics. In this case, if you assume it's square law, its IIP3 is very high. And of course, again, if you have mismatches, IIP3 will degrade. Okay. Okay. So what else do you know about this? So suppose you want to improve let's say the filtering at some frequencies. Okay. You want to remove some more undesired frequency components at the output. How would you do it without giving up on headroom? Okay. You can use what is called harmonic filtering. So we'll again go back to this guy. Except that instead of putting a current source, you're going to start putting LC tanks, and you can use multiple LC tanks. Sorry? So the main idea is, okay, what you could do is you could make sure, so let's say this LC is tuned to omega 1, this is tuned to omega 2. Okay. So at omega 1, this L1 C1 becomes an open circuit. Ideally you would have some very large resistance, let's say. Okay, so what that means is the current flowing through the output for that harmonic alone is suppressed. Okay, which means the current at the output is suppressed. So you can keep stacking this. The advantage is, of course, you lose very little headroom on your source side. Okay. Yeah. So that's why it's called harmonic filtering. And this is actually very commonly used in power amplifiers. We'll look at it in later in the course. Okay. Will look something like this. Okay, it's basically a degeneration. No, this is suppressing in the common mode. So once so at omega 1, right, let's assume this is an ideal LC tank. At omega 1, what is the current flowing through this tail? It will be 0, right? So at that frequency there can be no current flowing through this guy. Okay, no common mode current, obviously, right? There can still be a differential component. Differential component never goes through the tail anyways. Okay, so you're already assuming that it's a common mode. Okay. Yeah, of course, definitely. Anything you add in the common mode path can only give you a common mode rejection. It can't give you a differential mode rejection. Okay, then let's see. The last one we'll look at. Which one? Yes, this is actually a pseudo differential case, right? As far as DC is concerned, it's a pseudo differential case. Okay, so what happens at any other frequency other than omega 1 and omega 2? What is the voltage at this? This is a very low impedance. Remember, the parallel LC tank is a high impedance at resonance, low impedance at other frequencies. If you assume ideal LC tank, it is basically a very, very sharp characteristic, right? So you choose omega 1, omega 2 depending on what frequencies you want to reject. Okay, to give you an example, usually you could have, so through the common mode path, you want DC to flow, so you don't do anything about that. So let's say you want to get rid of 2 omega RF and 4 omega RF components. Okay, you can get rid of those. You can basically get rid of the harmonics of the omega RF. It's very useful for that, for sure.
There is ground noise.
Yes.
Not in omega 1 and omega 2.
Sure, this one doesn't do anything for ground noise. Okay, so this has nothing to do with ground noise directly. It may be a physical signal. I mean, it may be a real signal which is coupling through the ground path. Okay, so the last one we'll look at, it's called the multi-tannage GM stage. Have you heard of this before, the multi-tannage transconductor? You have? Sorry, you had an exam with this question or what? Okay, did you answer it correctly? No. Okay, so the reason it's called multi-tannage is because it started off with bipolars. Okay, remember that the transfer characteristic input voltage output current for a bipolar transistor is actually a tanh function. We looked at this a few classes ago, right? So the idea is you use multiple stages to create an effectively wider linear range at the input. Okay, so we'll look at the case for MOSFETs. Oh, actually I need a little bit more space. let's assume these are ratioed 1:1. Okay, these are ratioed, next one is ratioed 1:A, third one is ratioed A:1. Okay, and we're going to couple these guys. Let's see, how do we want to do this? Okay, this side and this side. Okay, this is how the output is connected. As far as the inputs are concerned, so let's assume this is plus or yes. Somebody had a question? No. Okay, this is plus and minus, again plus and minus, and plus and minus. Those are the RF signals, the input signals going in. So this is the ID. Yes, yes, it is unsymmetric, and that's what we're going to see. You're creating deliberate asymmetry to do something. We'll show you. So what is the characteristic for this one going to look like? Look something like this. Okay, what is the characteristic for this one going to look like? It's going to have some kind of offset. It's definitely going to have an offset voltage. Okay, so let's draw that with a different color. It's going to look something like this. Okay, and this is 2, and the third one is going to have some positive offset. Okay, yes.
3 and 2, they are like equivalent, right? Like
Except that one is going to have a positive offset, other is going to have, you're going to make sure one has a positive offset, the other has a negative offset.
with this connection it won't.
Why not?
They are just on top of each other. The nodes are
No, look at the connection for the last guy, the output connections.
one ratio is connecting to one ratio, A is connecting to A.
Yes.
So like it's one top of other. It is slicing the same circuit into half.
Input signs are.
Yeah, look at the input signs for A. So you either look at the input or look at the output. Yeah. Okay, so this is going to be VOS plus VOS, and you have a, let's say you have a minus VOS here. Okay, so let's say you now plot GM versus VID. Okay, so the first one is going to have a characteristic something like this. Okay, the second one is going to have a characteristic something like this. Okay, and the third one is going to have a characteristic something like this. Okay. So what is the overall characteristic, overall GM effective going to look like? So this is, of course, we are plotting GM. Okay, so your overall GM is going to look something like this. You get something like this. Okay. So you're effectively getting a wider input range, and that will translate to better linearity. Okay, from input to output. Of course, the reason you can see why it's called the multi-tan H, right? If you do the same thing for the bipolar, you will have multiple tan H curves. Okay, and you space them apart. No, this drain correction is fine. It's fine. Okay. Okay, and this is quite often you will see this used. Okay, this quite often used in many places. This is not the only place where you could use this GM. You could use this for in a lot of places. These are just general methods. Okay, so let's stop here. So and continue next class on Monday. So we look at the linearity and then the noise. Right, those two things we have left. Yes, it will. So you're definitely trading off linearity versus noise, and of course you are burning 3 times the current. Okay, so definitely. But what you could do, of course, you could have a lower GM and a wider range. That you could always do. You could reduce the current or the sizes, which is what you do on the other cases anyways, right? If you look at degeneration, you are effectively reducing the transconductance and improving the linearity. Okay, so that is what you do here also.